Welcome back, class. Today we will discuss the topic of the laws of algebra in a little bit more detail than we were able to do last class. And we will dive into the subject of negative numbers as well. Now, what motivates our interest into discussing the topic of the laws of algebra is that we found that there was some strange behavior when we tried to evaluate certain expressions using PEMDAS. We found that while you could take two or more numbers and add them in any order, such as say 1, 2, and 3. If I take 1 plus 2, I get 3. 3 plus 3 gives me 6. If I took 1, 2, and 3 and I start switching around the order, such as say doing 3 plus 2 plus 1, I'm still going to get 6 at the end of the day because 3 plus 2 gives you 5. 5 plus 1 gives you 6, right? And if I change my order again, maybe I start with 2 and then add 3 and then add 1. Well, 2 plus 3 is still 5. 5 plus 1 gives me 6. But it turns out that subtraction operators are not as forgiving. I can't simply take two or more numbers and switch their order when I'm performing subtraction. If I took, say, 4 and 1, well, 4 minus 1 gives me 3, but 1 minus 4, whoopsie, is going to give me one of those negative numbers, hence our discussion today. And what's interesting is that this idea of being able to switch the numbers around and maintain the actual quantity that you might be dealing with, it doesn't just apply with, say, the addition operation, but it also applies with multiplication. So if you took two or more numbers and you multiply them in sequence, say like 1 times 2 times 3, that's going to be the same thing as 3 times 2 times 1, and that's going to be the same thing as 2 times 3 times 1. But what's interesting is that if you took two or more numbers under division, you cannot just switch their order arbitrarily. I cannot just decide on a whim that I want to switch their order. 4 divided by 2 gives me 2, but 2 divided by 4 gives me 1/2. So the conclusion that we draw, apart from just being a little bit confused, is that some operations, some operators allow us a little bit more wiggle room to switch the order of numbers while maintaining the same quantity. Of course, what's going on here? Why is that the case? If we think about it, say you have 1 plus 2, and just think about this statement. Don't look at the math, okay? I understand you guys can do this in your head, but think about what this is saying. This is saying you can take, say, one ball and add it with two balls, right? Well, wouldn't that be the same thing as if you took two balls and added it with one ball, right? Because at the end of the day, you're going to be left with a pile of 3 balls. This is where we get the idea of equivalence. We say something is equivalent to something else when you have a quantity on one or the other side of the equal sign that has the same total value. So, for example, this 1 ball plus 2 balls, what you see right here, it doesn't look the same as this. In fact, they're mirror images of each other, right? They're in the opposite order of each other. But nevertheless, you're left with the same total at the end of the day. So it turns out that there's this algebra law, which we talked about last week, and we call it the commutative law. And this basically says that the order of a number under addition and multiplication does not affect with an A, the result. So we use this algebra notation, A plus B equals B plus A, to represent this idea that I can take any two numbers and add them in any order. This letter A, it's not just a letter, but we call it what is known as a variable. And it just means that it's a symbol that represents a number, okay? A is a symbol. Yes, we usually think of it like a letter, and we associate that symbol with a sound, i.e. the sound A. But in a math context, the same symbol represented by the letter A actually denotes some value, some quantity that we're trying to account for. In this case, the quantity can be whatever we want it to be. To be clear, this quantity can be whatever we want it to be. And we don't necessarily have to know beforehand what that quantity happens to be. This is critical. I don't have to know what the quantity is. Okay, I don't know what A is. You don't know what A is. A is just some number that is floating around in space somewhere. And the same thing is true for B. I don't have to know what B is. You don't have to know what B is. B is just some number. B could be 10. B could be 10 billion. And in fact, what we'll see is that even for negative numbers, the commutative law holds. So B could be a negative value as well. We'll get to that. It turns out the commutative law holds true for addition and multiplication. Very interesting. But it does not hold true for subtraction or division. So you can't have like 1 minus 2 minus 3. This would certainly not be the same thing as 3 minus 2 minus 1. And the reason that we need negative numbers is that we need to know what it means when you're subtracting past 0, okay? Like, using the ball example, if I start with 1 ball, I can't take 2 balls away and then take 3 more balls away from my original starting point, right? I'd be left with literally 0 balls. And so we need to understand, what does it mean when we keep performing successive subtraction operations past 0? Does it mean anything at all? Does it just mean that we don't get some sort of an answer that's nice and pretty, or what's really going on there? The same thing is true for division. Like, you can't obviously take 1 divided by 2 divided by 3 and just switch the order of these and get the same thing. Okay, these would definitely not be the same quantity at the end of the day. Now, another thing that we saw, and this was in one of the warning sections of the last video, was that the specific order of the operations is also important in certain PEMDAS contexts. And so, for example, if you have an expression 1 plus 2 plus 3, while we know we can switch the order of these numbers, what's also interesting is that you can actually switch the performative behavior of performing addition, performative behavior of performing addition. That's a little bit of a tongue twister. Maybe we would say it as, we can choose to do addition, more simply, in any order that we want, okay? I could say take the last 2 numbers and add it with the first. If I took the last 2 numbers, 2 plus 3 gives me 5, 5 plus 1 gives me 6. And what's going to happen is this is exactly the same as if you took the first 2 numbers and added it with the third number. You're going to get the same quantity in any case. Now, while we usually think of being able to perform these operations in any order using just certain symbols, such as the numeric symbols 1, 2, 3, so on and so forth, it's also easy to represent this using, just graphical methods such as the little hash marks. So if I represent the number 1 with a little 1 hash mark, and I represent 2 with the little 2 hash mark, and 3 with 3 hash marks, it turns out that this property of being able to add things in any order also is obeyed by the hash marks themselves. And so it doesn't matter the representation that we have for how the numbers look, the numbers appear to perform math the same way, and we get the same quantity. Either way we do this addition, we should get 6 little hash marks on either side of our equal sign, which is interesting. So the representation doesn't matter. You didn't have to choose, say, the symbol 2 and 3 to represent the quantities 2 and 3. You could have chose any symbol that you wanted to represent these values, and regardless, the actual operations themselves can be done in any order. That's very, very interesting. We call this property the associative law. This means that the operation of addition and multiplication may be done in any order. For a string of operations, those may be done in any order while maintaining the same value. So the formula for this is a little bit strange. You've got A plus the quantity B plus C, and that's equal to A plus B plus C. Now, this looks a little funny, guys, but all this formula is saying is if you can take any three numbers, and if you add the second two numbers, that would be the B and the C here. Those are my second two numbers. With the first number, which is represented by A, that's going to be the same thing as if I took the first two values or first two numbers represented by A and B and add it with the third number represented by C. Okay, so A, B, and C just represent some number. I don't know what A is. You don't know what A is. Nobody knows what A is. But if you take these numbers, you can add them in any order. And similarly, you can multiply these numbers in any order as well. So you can always take three values and perform multiplication in any order. And while we usually think of this as like just three numbers in sequence, you can actually demonstrate that this applies for any number of terms that you choose. So like, while obviously if we took three numbers such as 5, 10, and 20, while the associative law implies that we could add these three numbers in any order, and that's true, 10 plus 20 would give me 30. And by PEMDAS, we would then add the 30 with the 5, giving us 35. And this should be the same thing as 5 plus 10, which gives me 15. And 15 plus 30, I'm sorry, 15 plus 20 rather, should give me 35. There we go. So we get 35 either way. What's interesting here is that the associative law also applies if we started to break up each of these individual numbers. So like, 10 is the same thing as 5 plus 5. I hope everybody knows that 10 is 5 plus 5, right? So we could have taken this top formula that you see here and we could have rewritten it as 5 plus the quantity 5 plus 5 plus 20. And this would get us the same thing as 5 plus, well, 10 is 5 plus 5, right? Plus 20. And what's interesting is you can start to play around with this a little bit, but you will eventually discover that you can move around these parentheses really in any order. Because we broke the 10 up into 5 plus 5, it's very easy for us to start to see that, well, this here should be the same thing as this here. Because essentially all we did was we broke up 10 to be 5 plus 5. And then this quantity here is just saying add 10 with 20, right? Which would be like we added an extra set of parentheses around here. But suppose we didn't add those set of parentheses. Suppose we just put the parentheses around the 10. Well, we would still, at least in this instance, be able to add these four numbers in any order. And in fact, that's exactly what the associative law is telling you. It's saying that the order of the specific parentheses is arbitrary, meaning you choose the order of the parentheses whenever quantities are added in any specific order. Now, this is also true for multiplication. You choose where to put the parentheses, i.e. you choose the operations to perform first whenever quantities are being multiplied in sequence. But associative law does not apply for subtraction, okay? Or it doesn't apply if you've got instances where numbers are being added and subtracted. And it certainly doesn't apply for instances where you've got a mixture of different operators. So for example, let's just say you've got A minus B plus C. This would not be the same thing as A minus B plus C, okay? And it's not simply because We changed, well, actually, it's simply because we changed this symbol here to a subtraction. It really is that simple. So if we change that sign to a subtraction symbol, it's going to mess everything up. All right. Just an example of this. Let's let A be 1, B be 2, 3 be C. Sorry, C be 3, rather. This is not going to be the same thing as 1 minus 2 plus 3. They're absolutely not going to be the same thing. What you're going to have here is you would have 2 plus 3, that gives you 5. 1 minus 5 would not equal 1 minus 2 is going to be a negative value. And then you'd have that negative value plus 3. It would not be the same thing. They would not be the same totals at all. Okay. Another law that we need to know before we move on to negative numbers is what is known as the distribution law. The distribution law says that whenever you have three values, such as an A, B, and C, and you're adding two quantities and then multiplying by a third, then what's going to happen is a little bit strange. It's like you're going to take the value that's out in front of the sequence of parentheses and distribute it, meaning give it away. That's what distribute means. It means to give to someone else, distribute to these other terms in the form of multiplication. Now, why is that the case? Why does the distribution law work like this? And the answer to that question is, again, just pick three numbers, A, B, and C, and try to figure out how the numbers behave. So suppose we have a setup like my A is 1, my B is 2, my C is 3. What this is telling you to do, if we recall that a number out in front of the parentheses is the same thing as multiplication, is this is saying one set of 2 added with 3. So that's saying one set of 2 added with 3. What does that look like? One set of 2 added with 3. Well, here's my one set. Okay, it's just a bubble. It's one of something. What is that something? That's 2 and 3. That's what it looks like. Now, here's the interesting part. If you look inside the bubble, you see you've got one set of 2, and you've got one set of 3 inside of the bubble itself. So one set of 2 plus 3 is equal to one set of 2, which we could just say is 1 times 2, and one set of 3, which is the same thing as 1 times 3. So 1 times 2 plus 3 does indeed give us 1 times 2 plus 1 times 3. That's our conclusion. Now, if we change the A, B, and C, say I change my A to be, I don't know, 2. Okay, let's keep the numbers small, right? Because this is just an example. So my A is now a 2. I didn't change my B. I didn't change my C. I just have, two sets of 2 plus 3. What does two sets of 2 plus 3 look like? Well, I'm going to draw two bubbles because my bubble represents a set of something. And then two sets of 2 and 3. Here's my 2 plus 3. Here's the interesting part. Now you have two sets of 2 inside my bubble, but I also have two sets of 3 inside my bubble. That's the interesting part. So I'm gonna be left with two sets of 2 and two sets of 3. So 2 times 2 plus 3, well, is going to be equal to, what is two sets of 2? That's going to be 2 times 2. And two sets of 3 is just going to be 2 times 3. Of course, we can demonstrate this by increasing A to be 3, because why not? And if we do 3 times 2 plus 3, or we say 3 sets of 2 plus 3, here you're going to draw your 3 bubbles. You're going to put your balls or your marbles inside of the bubble. And I hope you guys can see that just like before, you're going to now have 3 sets of 2 and 3 sets of 3. So this is why the distribution law works. And because you can multiply numbers in any order, really, and A is just some number and B plus C is just some quantity that you could add together at the end of the day. Now, we know what B and C are, or what they happen to be in this instance, where I let B be 2 and C be 3, but we don't always know. But regardless, if we did know, we could switch the order of those operations, right? So because we know 1 times 2 equals 2 times 1, and really any two numbers multiplied together with each other can be done in any order, right? That was the commutative law under multiplication. Then what we can infer is that when we've got this distribution law, because B plus C is just some quantity, I should be able to flip the order of my A, and it'll be equal to each other. This is definitely true. Of course, B plus C, if it's multiplied with A on the right-hand side, that's going to look a little bit different, right? You're going to have a B multiplied with A and a C multiplied with A on the right-hand side. So, of course, the question in students' mind is, apart from simply arguing on a basis of the commutative law, that the distribution of the left-hand distribution should be the same as right-handed distribution, how can we find an equivalence between these two things? Well, one way to do that would be to start with left-handed distribution, which is this A times B plus C, and just write out A times B plus A times C. Then what you're going to do is you're going to use that commutative law. You're going to use the fact that we can multiply the A and the B and the A and the C in any order, and we'll just go ahead and switch the order. Well, we said that A times B is the same thing as B times A, so I'm just going to switch the order. And A times C is the same thing as C times A, so we'll switch the order of that. Now, I hope you guys can see that this left-handed distribution setup is exactly the same thing as what we have here. And so for that reason, we can say that there is, in fact, an equivalence between right-handed and left-handed distribution. Now, before we get into the subject of negative numbers, I do want students to be aware of one. Start here. Now, before we get into the topic of negative numbers, I do want students to be aware of one interesting fact about the world in which we find ourselves in, i.e., the material world around ourselves. And this is called the quality quantity problem. And this problem can be stated as, just very simply, when does a pile of sand become a sand dune? Okay. When does a pile of sand become a sand dune? When you start to observe physical phenomena in the world around yourself, it becomes very difficult for everybody to agree upon what number should be associated with the quality of something. So, for example, a quality being something like the color red. Color would be a quality of an object. An object has a color. But how would you describe the quality of redness to a computer? Well, if I was to describe the quality of redness to a computer, I might start by thinking maybe we can assign some number to red itself. And then obviously we would assign blue, the color blue, another number, because computers can kind of make sense of numbers in the sense that we could have an algorithm, if you will, that would be able to perhaps manage this information. Presumably, we could start to train the computer to identify red or blue. But if I went to another computer, or if somebody else was programming their computers and they were trying to teach their computers what red, quote unquote, what the quality red was, or what the quality blue was, they might assign the color red to some totally different number than what I assigned the color red to. And they would be just as valid in the sense that I arbitrarily chose a number to represent red, and they're arbitrarily choosing the number, a number to represent red. Said another way, there might be an objective truth to the number one when we write the symbol on a paper and we've associated this symbol with this abstract idea that there is one of something in the world. Maybe there's one tree that we're trying to represent with this number one. But there's no objective truth to assigning a number to a quality. Okay, and that's the problem. That's essentially the problem of quality versus quantity. So it's very hard for us to start to assign numeric values to certain qualities that you might see. However, that being said, binary phenomena may be analyzed mathematically by assigning a positive or negative symbol to indicate the quality of an object. Okay, binary phenomena. What the heck does that mean? Binary phenomena. Well, phenomena, I hope all students in the class know the word phenomena. It means something that we're observing, a thing happening in the world around us. It's a fancy Latinate word that just means something happening. Binary, the word binary, bi is the Latin root that means two. Ary means numbers. And really, binary in English is a word that we refer to mean two things. So whenever you have a phenomena in the world and it has basically only two states, only two options, black and white, daylight, nighttime, hot, cold, up, down, left, right. These are all binary phenomena. They exhibit the property of what is known as polarity. Okay, there's only two options. Either something is up or it's down. Either something is left or it's to the right. Either something, and these opposites are in opposition to one another, which is why we say it has polarity. So just to draw a picture, here's distance, and we can use the idea of positives and negatives to describe moving in a certain direction. If I want to say move in a eastward direction, I would use a positive symbol to describe that movement. And if I wanted to move in a westward direction, I might use a negative symbol to describe that movement. Now, regardless of whether we're moving to the east or to the west, students will know that, if I travel from Lincoln to Omaha, it's roughly 45 miles away. Okay, maybe a little bit more than that, but it's roughly 45 miles. And it doesn't matter if I'm traveling from Lincoln to Omaha or from Omaha to Lincoln going west, right? I'm still traveling 45 miles, but I'm traveling that 45 miles going in a specific direction. So the negative sign, this, what we're calling a negative, this little minus symbol or subtraction symbol, that's going to be able to allow us to describe the quality of moving in a specific direction. But then also you might be dealing with like a chemistry exam, and you're gonna see in chemistry there's this thing called electromagnetism. And electromagnets exhibit the property of polarity. So there's a positive pole of an electromagnet and there's a negative pole of an electromagnet. And we use this idea of positive and negative to represent that there's stuff moving in one direction, basically around this object, this electromagnet, and then there's stuff moving in another direction, in an opposite direction of the electromagnet, or said another way, that the force fields of the electromagnet point in two opposite directions. Another really important use for negative numbers happens to be in finance, in the field of finance, and specifically with respect to debt. Now, I hope students in this class don't have any debt. I hope that the debts you have are very small, because debt is a very, very bad thing for you to have. And historically, of historical note, if you didn't pay your debts back, you would not only go to jail, but you might be made into a slave of someone else. It was very common in the Roman Empire for people to be enslaved because they did not pay back their debts. And the thinking there was, well, if money represents your work and or the value of your production in the society around yourself, like you produced $100 of something for you to have $100 in your hand. Okay, just theoretically, assuming you're not a bandit, assuming you didn't go to war in like sack a city and just loot the place and get $100, assuming you obtain that money legitimately, then the thinking is, because you obtain the money legitimately, if someone owes you a debt, it's like it represents you gave them some of your life force, you gave them some of your time, some of your energy that it took you to produce money, and then they need to pay that back. Okay, but if they don't pay that debt back, then because maybe they're unable to, then well, you're going to have to take a little bit of their life energy, right? Well, life energy, that's kind of this notion that's metaphysical. You can't physically take someone's life energy. So what does that look like? Well, it looks like slavery. Slavery is where you rob someone of their vital life force in the form of their time on earth in exchange for their production. Okay, like your slave is producing something for you. That production represents a positive balance on your accounting sheet, on your balance sheet. That's your income. That's coming into the bank account, right? So, when someone's in debt back in the day, and even to this very day in some Asian countries, you could be enslaved for not paying back a debt. A fact that students should know about slavery is that, historically speaking, the vast majority of slaves on the earth are debt slaves. Even in this very day, people enslave themselves because they're trying to pay back a debt. It's something you always should be aware of when you're dealing with banks, because there's always the possibility that that social practice might return at some time in the future. Now, getting back to the class, we may represent debt on a balance sheet as you owing a specific amount of money in the form of a negative sign. A negative, this is a negative number. And in the context of debt, it describes, or in the context of finance, rather, in money, it describes you owing some amount of money to someone else. So this minus 100 would represent you owing $100 to someone else. If I wrote minus 5 in the context of money, that would represent me owing $5 to someone else. If I wrote minus 10, negative 10, that means I owe someone $10. Now, the long and the short of it is, there are a number of properties that emerge from negative numbers. I highly suggest students pause the video and write this down as just kind of a cheat sheet. Whenever you subtract two numbers, this is equivalent to adding the negative of some value to an original number. A and B represent any two numbers, right? So A can be something, B can be something else. When I have a negative B and I add it with a positive A, whatever that A is, that's the same thing as just subtracting B from A in the first place. In terms of money, you can think of it like, if you have $100 in your bank account, but you take out 50, you would have $50 remaining. If you have $100 in your bank account, but you owe a bank $50, you got to pay back that debt, guy. You got to pay back that debt. And so after you pay the debt off, you're going to be left with a balance of $50. All right. Another property of negative numbers is that when you multiply a positive with a negative, you're left with a negative result. And if I take a negative and I multiply with a positive, I'm left with a negative result. So how can we explain that? Well, when you take a negative number and you multiply, I'm sorry, if you take a positive number rather, and I multiply it with a negative, you might think of this as sets of debt. Sets of someone owing you some money. So like 1 times 2 is 1 set of 2, right? But if I do 1 times a negative 2, this is 1 set of a $2 debt. It's literally what it means, 1 set of a $2 debt. Well, what would 1 set of a $2 debt be? If you drew it pictorially, you could think of it like being this bubble, and inside this bubble, you have 2 little dollar bill signs to represent the $2 that someone owes you. And because they owe you that money, maybe we put a little minus sign in front of the dollars. So I hope you can see that it would in fact be a negative quantity at the end of the day to represent that set of $2 debts. If you have a negative number multiplied with a positive, you could think of it like groups of people who owe a debt X times. Groups of people who owe a debt X times. So if I do -2 times 3, it really means that you've got 2 people who owe a debt three times over. So if you drew that out using a bubble, we'll put a negative sign out in front of the bubble to represent that it's these 2 people that owe us a debt. And each individual has a debt 3 times over. So here are 3 little dollar signs. Well, in total, that should be $6 worth of negative dollar bills, right? I mean, they owe a debt of $6. Said another way, a debt, just a debt of $6. There are 6 dollar signs inside of these bubbles, and each one has a negative attached to it because the people owe that money to someone else. So -2 times 3 gives us -6. The last property of negative numbers is that whenever you multiply 2 negatives together, you get a positive answer. If you take 2 negatives and you multiply them together, this is equivalent to saying that you are effectively clearing a debt. This represents clearing a debt. Why does it represent clearing a debt? Consider multiplying -3 and -2 together. If -3 says, I'm removing 3, the multiplication symbol means sets, and the -2 on this end represents debt. You say, I'm removing 3 sets of $2 of debt. That's literally what -3 times -2 would represent. It says, I'm removing 3 sets of $2 of debt. So what would that look like? Well, here's 1 set, and here's $2 of debt. Here's another set. Here's $2 of debt. Here's a third set. Here's $2 of debt, and we're removing it. We're removing the debt. So in total, if you remove the debt, you would just be left with the remaining dollars. And you can think of it like, well, when you borrow money from a bank, say I borrow $100 and go buy my groceries. I buy exactly $100 worth of groceries. You would say I have a debt of $100 to the bank, correct? Well, if at some time in the future the bank decides, hey, we're good, we're square, you don't have to pay back the rest of that loan, what it means is that I have $100 worth of goods for free from the bank. It means that if I started with no money and I borrowed a debt of $100 from the bank, but all of a sudden they decided to remove that debt for one reason or another, I have $100 worth of assets at the end of the day. That's a positive, at least from my perspective. From the bank's perspective, they would see it as you're stealing from them. Okay? It would be unconscionable back in the day for banks to remove a debt from people. And usually back in the day, there weren't these institutions called banks in a formal sense. Instead, what we see, especially in Babylon and Samaria, is that the priests and the temples were actually where financial transactions took place, because everybody went to the temple. So you can imagine, this guy who's totally loaded, he goes to the temple and his temple buddies ask him for some money. And that's kind of how the practice started. So all of the financial transactions in ancient Samaria eventually went through the priests. This is also why you see in biblical sources, such as the New Testament, Jesus famously coming into the temple and throwing out the rabbis, if you will. Okay, that was the symbolism of that action in the New Testament. At any rate, I hope everybody understood what was happening here with negative numbers. And we're going to have a lot of practice in class, so I'll see everybody there. There's not too much more to know about negative numbers, so we're kind of just going to blow through this section. We're going to look at some PIMDOS problems that incorporate negative numbers in class for sure, just so that you guys don't get sideswiped by the homework problems. But I think pretty much everybody should be set to go. Take care, guys.